In this video, we are going to learn how to do triple integrals in cylindrical coordinates. So if I have some triple integral of some function, f of x comma y comma z, over some three-dimensional region D, and now I make a substitution, and I'm going to do a change of coordinates. We're going to get a very similar formula to what we saw with double integrals. So if I'm subbing in some formula for x, I'm going to call this function g. It might involve three variables, which I'll call u, v, and w. And if I sub in other things for y and for z, then my triple integral will now transform. Once I've subbed in, it'll be over some new region g. There's going to be this Jacobian term in absolute values. And the Jacobian is very similar to what we saw before with double integrals, except now, because there's three variables, I'll have a 3 by 3 matrix, where on the first row, we'll take all the partials of x with respect to u, v, and w, and then the partials of y, and then the partials of z. Okay, so let's take a look at what this would become for cylindrical coordinates. So in cylindrical, remember x is r cosine theta, y is r sine theta, and z is just z. So, okay, it's kind of like r is taking the role of u, theta is taking the role of v, and then z is taking the role of w in this formula. I encourage you to check it, but if you do all the partial derivatives now, you'll end up getting this for your matrix. So I briefly just want to talk about how do you do a determinant of a 3 by 3 matrix. What you do is you pick one of the rows or columns to do what's called expand along. So if I pick this first row, I take the first entry of that row, which is cosine theta, and I'm going to write that down. Cosine theta. And then you cover up the row and the column that that's in. And that leaves you with this smaller 2 by 2 matrix, which I'm going to write down. There's one typo here. I forgot to put the r in front of the cosine, so let's add that in. And then I get the smaller 2 by 2 matrix that I then take the determinant of. That's what these vertical lines mean. Okay? Now I go to the next entry of that row, which is negative r sine theta, and I'm going to write that down. So I'll write down negative r sine theta. I'll cover up the row and the column that that's in, and the remaining entries I put into a 2 by 2 matrix. As I'm doing this, as I'm writing each of those entries down from that top row, I alternate signs. So I put a plus in front of the first one, and then a negative in front of the next one, and then it'll be a plus in front of the next one, which is 0. Okay, and when you cross out the row and column zeros in, it leaves us with this 2 by 2 matrix. And now we know how to do a determinant of a 2 by 2 matrix. So let's see, I got that cosine theta in front. And then I multiply these two entries, which gives me r cosine theta, minus multiply the other two diagonals to get 0. And then here, this double negative becomes a plus r sine theta. Now multiply that determinant. So multiply these two entries to get sine theta. And then minus the other two diagonals to get 0. All right, and then I got plus, well, 0 times anything is just 0. So that last term just becomes 0. And if I multiply this out, let's see, I get r cosine squared theta. From the next term, I get plus r sine squared theta. And then I could factor out an r. Cosine squared plus sine squared becomes 1. So that's just r. Okay? And I can take r to be non-negative when I use cylindrical coordinates. I can always set it up that way. So when I do the absolute value of my Jacobian, the absolute value of r just becomes r. Okay, so much like in polar, our Jacobian in cylindrical just is r. So I'm going to write that here. Just r. And then my new variables are, I got that dz, that dr, and d theta. And as we'll see with an example in just a sec, we typically do these cylindrical coordinates in this order. Okay, so let's look at an example. Let us flip this thing to the next page. And up top, I have a description of how we're going to deal with those limits of integration, but I think it's easiest to explain that as we work through the problem. So I want to find the volume of the region in the first octant bounded by these two equations. So let's first remember that if I want to do volume with a triple integral, I do a triple integral over my region, which I'll call it d, triple integral of 1. And then I write dv to represent that's a triple integral. So what I need to know is, well, what does this region look like? So I can find the limits of integration. So let's draw a picture. I'll draw my z-axis, my x-axis, and my y-axis. And I'm actually going to draw this twice because after I draw an initial sketch, I'll try to draw the picture a little bit better after that. So I'll refine it as I go. So let's think about these. I know x squared plus y squared equals 1 is normally a circle, just of radius 1 on the xy plane. Okay, so, but because I'm in the first octant, that's the portion where x, y, and z are all positive. So just like over here, it wouldn't be that full circle. It would just be like the quarter circle where it's 1 and 1 on those axes. But because there's no z in this, that means z could be anything. So at any point on this circle, z could be anything. I could go as low or as high as I want. At any point, I draw lines like this up. And that, instead of just a circle, I will draw in those lines. I'll draw in those lines up. And it creates a cylinder. It creates a cylinder. So that's what the graph of this actually is in 3D space, which is what we're working with. Okay. In fact, it's not a full cylinder. It's actually just a quarter of a cylinder. All right. My other equation, z equals y plus 1. Well, that's the equation of a plane. But to start drawing it, let's just focus on, let's ignore the x for right now. This would ordinarily be the equation of a line in the yz plane, where 1 is the z-intercept. 1 is the z-intercept, and then the slope of this is 1. So if I draw a line, slope of 1, something like this. And now to turn it into a plane, from this point and this point, I draw a line parallel to the x-axis, the other direction. X can be anything here, so I got to go in the x direction. So I draw a line in the x direction. Even from here as well, I draw a line in the x direction, parallel to the x-axis. And then I connect them, and it's looking something like this. Okay, so something like this. So this plane is going to slice through the cylinder. And when it does, well, there's this kind of point where it touches the cylinder. There's another point here. And then the cylinder is curved. So I'm going to make like a curved path connecting those points. And now I'm going to do my best to kind of refine this picture and draw a new version of this on the side. Okay, so I'll have this kind of circular base hitting 1 on the y-axis, 1 on the x-axis. And then I'm going to draw this line up. Okay. And then I'll have this line here for the back edge. That's hitting where z is 1. And then I'll have this line, this purple line, part of my slanted plane. Kind of going somewhere there. And then I'll have this orange dotted line that I drew. So that orange dotted line kind of curves and it connects those. And then I have this part of the cylinder going straight down. Okay, so this is something that, as we practice with it, we'll get better at drawing sketches like this. But nonetheless, my picture looks something like this. So now I'm ready to try to set up my triple integral. Before I do that, let me briefly talk about, well, how do I know I'm going to need cylindrical here? One of the tip-offs is that my base is part of a circle. So much like with polar, when I have circular regions, that's a tip-off to try polar. This cylindrical is the same thing. When I have circular portions, that's a tip-off when we're in 3D to try cylindrical coordinates. Okay, so let's talk about our integral. So I'll have my triple integral where the function 1, well, there's nothing to sub in for it. It just stays as 1. And I know that when I do my cylindrical, the dv, remember the Jacobian is just r. And then I got to write some other variables, my dz, my dr, d theta. We pretty much always do it in this order in cylindrical. So because dz is inside, I need to know these limits of integration in terms of what z equals for this innermost integral. And I do that by drawing an arrow parallel to the z-axis, thinking about when does it enter the region and when does it exit. So it'll enter through this bottom on the xy plane, and it'll exit by bursting out of this slanted plane. So it's entering that xy plane equation is z equals 0, and it exits by hitting this equation surface, which I already have that equation. It's z equals y plus 1. Okay, so that lower limit of integration z equals 0. And for the upper one, I don't want to write y plus 1 because I'm trying to get rid of the y's as the variable. So I need to convert this y using my cylindrical stuff. So y is r times sine theta. I get r sine theta plus 1, so that's what goes here. Z equals r sine theta plus 1. So I need to think about my other two limits of integration and find those limits. So I do that by drawing the shadow of my solid object on the xy plane. And the shadow, what I get when I project it straight down, well, that's just going to be this base quarter circle. So that base quarter circle. So I'll draw another picture real quick just of that shadow on the xy plane. So the shadow on the xy plane forms that quarter circle. So this quarter circle hitting 1 on the x-axis, 1 on the y-axis. Okay, that's that base region. And then to figure out those limits of integration, I draw an arrow radially outward. So radially outward. And then when does it enter the region? Well, it enters it right away. And that's when r is 0. So that's my lower limit. And then it exits the region on the circle. And the equation of the circle is r equals 1 because the radius is 1. And then finally, my values for theta, well, the smallest value of theta is over here. That's when theta is 0. And then the biggest value of theta is over here. That's when theta is pi over 2. Okay, so I got my triple integral. We're ready to try to evaluate it. So let's focus on the innermost integral first. So the outer ones stay as they are. So 0 to pi over 2, and then 0 to 1. So the innermost integral has z as the variable, because it's dz. That means I treat r as a constant. So that antiderivative would be rz. And then I got to plug in the z equals 0 and z equals r sine theta plus 1. And I'll still have the dr and the d theta. Okay, so let's see. I'll get my double integral. I got 0 to pi over 2 and then 0 to 1. So if I plug in this whole thing in for the z, well, the r is going to get distributed to each of these terms. And that's going to give me r squared sine theta plus r. Okay. And then I got to subtract what I get when I plug in the 0 for the z. But that's just going to give me 0. Nice. And then I still have the dr and the d theta. So next up, I'm trying to do the integral with respect to r as the variable. So I'm thinking of theta as a constant. Okay, so that's going to give me my outer integral is 0 to pi over 2. And then I'll get r cubed over 3 sine theta plus r squared over 2. Okay, and then I'm going to plug in my r equals 0 and r equals 1. And then have that d theta on the outside. Okay, so I'm ready to plug these in. I get my outer integral from 0 to pi over 2. If I plug in 1 for r, I'm going to get 1/3 sine theta plus 1/2. And then I got to subtract what I get when I plug in 0. When I plug in 0 for r, well, both of the terms just become 0. Nice, and then I get d theta. Okay, so from here, I've gone ahead and written out already what the next steps of the integral are going to be. Because I mostly wanted to focus on the setup and doing the first couple of integrals because those are the toughest. And from here, it's not too bad. The antiderivative sine is just negative cosine. The antiderivative 1/2 will be 1/2 theta. From there, I'm ready to plug in the pi over 2 into both of these. And that gives me this. And I can plug in 0 into both of these. And that gives me this thing in the parentheses. And then the double negative becomes a positive. So we just found the volume using cylindrical coordinates. There's no units given. So the best I can do is I could just write that this is in units cubed for volume. Okay, and there we have it. We just worked out our first cylindrical coordinates example. So the key takeaway is that cylindrical coordinates are nice when our region of integration involves circular things. So things like cylinders, like we saw here, or as we'll see in later examples, things like paraboloids and cones, really nice for cylindrical coordinates.